Now let's put some numbers to our freezing point depression as well as to our boiling point elevation. We know that when we dissolve a solute in a solvent, the freezing point should decrease. Whatever was the original freezing point of the solvent, now it should be lower. But by how much? There is a very simple equation for the freezing point depression where delta TF, F stands for freezing point, and delta T means change in the freezing point temperature. So change in the freezing point temperature equals to Kf times M. Kf is a unique freezing point depression constant and it's unique to every solvent. So water has its own unique freezing point depression constant. Ethanol has its own unique freezing point depression constant, and so on. M stands for the molality of our solute particles. Notice I did not say molarity but molality. We specifically use molality because, as said in the previous video, using molality makes us temperature independent. Now what we are looking at is not the concentration of the solute but rather the concentration of the solute particles. How are those two different? For example, if you were to dissolve 1 molal, if you had a 1 molal sodium chloride solution, but when you add that sodium chloride to water, it actually dissociates into sodium ions and chloride ions. So every 1 sodium chloride gives you 2 particles. So if you had a 1 molal solution, in reality the solute particle concentration is 2 molal, and then you would plug that in this equation 2 molal, and using water's unique freezing point depression constant, you can find out how low would the freezing temperature go. Similarly, here is a situation for the boiling point elevation. The equation for boiling point elevation is very similar to that for freezing point depression. So here is the change in the boiling point temperature equal to the unique boiling point elevation constant Kb times the molality of the particles. Let's look at a few problems dealing with this situation. So ethylene glycol, and here is the structure of ethylene glycol used in automobile antifreeze. You have a solution of ethylene glycol, an aqueous solution, meaning water is the solvent, and the concentration of ethylene glycol is 8.38 molal. So calculate the freezing point, the new freezing point of our solution, and also calculate the new boiling point. Well, if the freezing point is going to be depressed, we expect the new freezing point to be lower, and if the boiling point will be elevated, we expect the new boiling point to be higher. Now here is the unique aqueous water Kf value. We earlier said that there is a unique value for Kf as well as Kb for a particular solvent. For Kf, when it comes to water, it's 1.86 degrees Celsius over m. That's the unit for the Kf. Multiply that by the molality of particles. Ethylene glycol does not break down into 2 particles. It's a molecular compound. So for every 1 molecule of ethylene glycol, there is 1 particle. Hence we keep it as 8.38. And when we do the math here, our freezing point should change by 15.6 degrees Celsius. The problems in this particular topic use temperature in degrees Celsius. When we were studying gas laws, we were using Kelvin. Keep that in mind. Now, since the freezing point is depressed, the normal freezing point is 0 degrees, 0.0 degrees Celsius. The new freezing point should be lower by 15.6 degrees, and it should be negative 15.6 degrees. What about the boiling point elevation? When it comes to the boiling point elevation, the value of Kb is 0.52 degrees Celsius over m. Recall that the equation for Kb, for the equation for boiling point elevation is delta Tb equals Kb times m. Kb value here is 0.52 degrees Celsius over m. So the new boiling point should be higher by 4.4 degrees Celsius, whatever it was originally. So the new boiling point is 104.4 degrees Celsius, because the normal boiling point of water is 100.0 degrees Celsius. Here is one more problem. Calculate the freezing point of a 3.00 molar aqueous solution of calcium chloride and the boiling point of the same solution as well. Now calcium chloride, unlike ethylene glycol, when we dissolve that in water, it will break up into calcium ions and chloride ions, one calcium and two chlorides to be exact. So we get 3 particles per 1 formula unit of calcium chloride. So if we have a 3 molar solution of calcium chloride, that gives us a 9 molar particle solution. And then the rest of the process is the same. We apply the equation to find the change in the temperature of the freezing point, which is lower by 16.7 degrees, and similarly for the boiling point the temperature goes higher by 4.7 degrees.